we're very happy to have Jonah Kudler-Flam from IAS and TCTS, who will tell us about horizons as eavesdroppers. All yours, Jonah.
Thank you very much for the invitation and for coming. First I'm going to apologize because I know you've heard about some work a couple months ago from one of my collaborators, Gautam. This is some follow-up work on what he talked about, but it's mainly a reinterpretation of that work in terms of the theory of quantum error connection. Okay, so I'm going to first go through the review, which might be a review for everybody here, but if you are that talk. So let's consider an experimentalist, Alice, who maintains a spatial superposition of a charged particle. And say she had put a charged particle through some Stern-Gerlach apparatus and gotten some spatial superposition. And she wants to recombine the superposition in a finite amount of time as to minimize the decoherence. So this is just a picture. We have some spatial superposition, and she has some finite time to recombine the particle. So there's an adversary, Eve, who tries to decohere Alice by measuring the Coulomb field generated by this particle. And if Eve is able to gain which path information, then she is necessarily entangled with Alice, and hence succeeds in decohering Alice's particle. So yeah, in this picture, Eve is at space-like separation from the recombination event, so it's not measuring the radiation from the recombination event, but it's just measuring the Coulomb field. So these two trajectories source two different Coulomb fields, and you can imagine Eve releasing a particle from a trap. It'll be deflected in different ways depending on which trajectory of the wave function Alice's particle is on, and then Eve could measure at a later time where that particle ends up to try to figure out which path Alice's particle went on. Because she's at space-like separation from the recombination, causality just ensures that she cannot affect Alice's decoherence. So there's a bit of attention initially, just thinking about her being at space-like separation and not being able to affect the decoherence, but also being able to measure the which path information. So there's going to be some trade-off between how much which path information she can gain and how much Alice has to decohere. So the global state, including the electromagnetic field now, looks like this. I've just added in some state I've called psi left of the electromagnetic field, corresponding to the particle going to the left, and the corresponding one for the particle going to the right. So let's first just look at this and think about if you just take a partial trace over the electromagnetic field. If you do this at some finite time, then this is some 2x2 density matrix for Alice. And the off-diagonal elements are going to be nearly zero because these two electromagnetic fields are nearly orthogonal. But this is not the decoherence we want to think about, and this is what some people have called false decoherence. So the decoherence we're interested in, the reason this is not the interesting decoherence is then Alice could have just recombined her particle and maintained and the Coulomb fields would then look the same at a later time, but she just maintained coherence. And so the interesting decoherence that we want to look at is the decoherence due to radiation, the stuff that she can really never get back. And so to isolate this true decoherence, it's convenient to go to asymptotically late time. So now we're in the state of the electromagnetic field at null infinity, and this is Alice's particle at a future time like infinity. And so we define the decoherence as the magnitude of these off-diagonal elements, or 1 minus the magnitude of these off-diagonal elements.
But then the question, wouldn't like reversible decoherence or something be better terminology than false decoherence? Like it really has decohered, and if you had to instantly like try to do something locally to tell, then you wouldn't be able to get the phase information because it genuinely has left the local region. It's just that by slowly bringing them back together, you can undo that decoherence process.
Sure. So this Alice is decoherent, but if you take Alice and you consider Alice to be the particle plus the quantum fields around her, that hasn't decoherent.
Yeah.
So this is just the distinction. But yeah, I mean, in that sense, sure, it's decoherent.
Is there some way to quantify? I mean, if the particles were just separate all along from the beginning, I mean, if the one particle was in superposition from the very beginning forever, and Eve had a lot of time, then presumably it would be true that Eve would be able to distinguish. I mean, would be able to measure which field it is, right? So one way to understand why Eve might not be able to do it, presumably would have to involve the fact that she has only access to some finite region of space, and that maybe the two states are not nearly orthogonal in the sense that the reduced density operators in that region that Eve can access might be distinguishable.
Yeah, I think you're pointing to this trade-off between if she shouldn't be able to influence the decoherence by causality, but if she is able to measure for a very long time, it seems like she can distinguish these two paths.
Yeah. So is there some obvious relation between how long how much time you need to give Eve? I would expect that it's probably more time than the light crossing time to the particles.
Yeah, so the next slide I'm going to review like the back of the envelope resolution to this. That's just shows the order of magnitudes of stuff. That shows that Eve really can't decohere Alice as much as Alice has to decohere herself from her recombination event. But then it can be, all of this can be is very natural when we put it in the language of quantum channels in there. But yeah, this trade-off that you said is exactly what the first kind of resolution to this tension is. So these two states at infinity are going to be coherent states in in this approximation. These are like classical charge current sources, and so the corresponding fields are going to be coherent states. And this will be at infinity e to the minus expectation value of the number of particles or photons radiated to infinity between the two states. So when the number of photons becomes order 1, the decoherence becomes large, which makes sense. If you detect a particle in one state, that means that you decohere.
Sorry, but you're going to detect the particle only due to radiation, which is not going to happen unless we have a time-dependent process.
Yes.
I was asking about a time-independent situation. So I don't think that's how you're going to answer it. I don't think quite answered my question.
Let me just go back to this picture. So, so for a very long time, Alice has had this particle in some superposition, and Eve can measure this Coulomb field. And so, if given enough time, you would think she can distinguish these two paths by measuring the Coulomb field.
Yeah, but I suspect she'll need more time than it would have taken her to just look at where the particles are.
Right.
But yeah, I was just curious whether that was also something to check.
Yeah, so there's really two perspectives. You can either think of it as the perspective of Eve distinguishing these paths due to the Coulomb field, or you could think of it as the radiation that has to be done during this recombination event.
Yeah.
It depends on how well Eve can measure the position of her detector particle, right? So like, if she can measure arbitrarily well, she could instantaneously
No,
distinguish
that's not true, because she has access only to a small region of space.
Well,
So the two states that you're looking at will be distinguishable in a small region of space, because they'll reduce to almost the same density operator.
well, there'd be a differential force condition on which state the
Yeah, but it's
source.
dominated by fluctuations.
Right, so the fluctuation.
So, yeah, so in these earlier papers, I'm going to outline this one. Alice's experiment is limited by the radiation during the recombination event. If you never recombined, nothing's ever accelerating, and you're always going to have a pure state for Alice. And this can be estimated as the charge of Alice times the distance in her separation over the time of her recombination event, so that's squared. And so to maintain coherence, she wants to do her recombination slowly enough such that the number of particles is small. And from Eve's perspective, there's some vacuum fluctuations of the electromagnetic field. This is related to what you're saying, that she can't really distinguish how much her particles have been deflected any more than just how much the vacuum fluctuations are, if given a time that's less than this distance away, this light crossing time. So basically, what's learned from this paper is that you can't simultaneously have no decoherence due to doing this slowly enough, and also Eve getting enough information because she's able to detect something more than just vacuum fluctuations. So the conclusion from these papers is that Alice must decohere herself as much as Eve can decohere her by measuring these Coulomb fields. So this is it's natural to ask, was this really the best experiment that Eve could have done to do decohering? I just suggested releasing some particle from a trap. You could imagine releasing many particles from traps and doing some larger global measurement. And for consistency, you would just need that no matter what Alice does outside in this space-like region, it can't give more decoherence than the amount of decoherence in this recombination event. And this is the point where it's very natural to start thinking about this in quantum information theoretic language instead of thinking about these explicit examples of deflection of particles. So to do so, let me just review what quantum channels are. So in general, a quantum channel between two states is it's a map between density matrices to density matrices, and you can think of it as you take your original density matrix, you add in some ancilla, you do some global unitary evolution to both of these together to couple them, and then you lose some information about part of the system. So here, this is some map from Alice to some Hilbert space HB, which you can think of as Alice's particle plus the fields around her. But maybe she's traced over Eve's quantum fields. So she's maybe lost some information to Eve. There's a complementary channel where instead of tracing over Eve, you're tracing over Alice. So this is like the quantum state from Alice's initial state to Eve's state. So there's a channel, the first channel is Alice's state to Alice's state, and the second channel is Alice's state to Eve's state. And information in quantum mechanics is conserved, and so so if information goes to Alice, then it can't go to Eve, and if information goes to Eve, it can't go to Alice. We have no cloning. So in this language, it's useful to have a more general definition of what decoherence is. And so instead of just being the off-diagonal elements of this density matrix. And so we would say that Alice has not decohered at all if there exists some channel that reverses the quantum channel of her experiment. So if she does this recombination, she does whatever she wants, if there's some fixed channel that she can apply that just completely restores her initial state, then she hasn't decohered at all. This naturally gets rid of this false decoherence that was mentioned earlier. Usually this is not you can't perfectly reverse something unless you have some unitary process or some other special kind of channel. But when perfect recovery is not possible, we want to define some amount of decoherence that's more continuous. So it's natural for quantum channels to define a norm called the diamond norm, which we're going to be interested in the diamond norm between this channel with the decoding channel to the identity. So you can think of this as just what's the worst that can happen for all of the initial possible states of Alice. So if Alice starts with any of her initial states of her qubit system, what's the worst that happens in terms of her decoherence out of all of those states? So there's some, pesky soups and whatnot. But yeah, so this is our new definition of decoherence. Okay, so clearly this works more generally than the setup that I recently just talked about, and but you can actually go compute this diamond norm in this simple example, and it's consistent with the previous definition I gave, which is the 1 minus this overlap. So in this case, they're exactly the same, but people from quantum information have proven things using this kind of definition of decoherence, so it will be useful for us. So now we want to define what information is to Alice. What information is going to Eve. So we've defined what it means for Alice not to decohere. And for Eve to have information, this means that Eve is able to distinguish the two paths. And so the natural measure of distinguishability is the trace distance. So if you have two states, you can distinguish two states if they have some large trace distance, which is just the one norm between the difference of the states. And operationally, this means that you can make a single measurement and with high probability know which state you have. And so with this, we define the information available to Eve as this maximum trace distance over all of Alice's initial states. So it's also some diamond norm. So here, remember, this is the recovery. This is the complementary channel, the channel that sends Alice's initial state to Eve, and then this is just some fixed channel, some channel that sends every possible state of Alice to just some fixed state of Eve. For computations and for some other reasons, we actually look at this this fidelity quantity. It's not the standard fidelity, not the Ullmann fidelity, but it's sometimes called Halelo's just as good fidelity. And it's equivalent to the trace distance in the following way. It both upper bound and lower bounds the trace distance. So we can actually go compute this, and so in practice we're going to look at the fidelity. Trace distance is a bit more challenging. But you can see that fidelity is close to 1 when trace distance is small, and fidelity is close to 0 when trace distance is large. So they're essentially equivalent. So really, the guiding principle is something called the information disturbance trade-off. This theorem, which has come in different forms, but we'll use this theorem by these authors. And this is the following statement. It says that the information, as we have defined it, which is this central quantity, is both upper and lower bounded by the decoherence of Alice. So this guarantees that for any quantum channel, if Alice has not decohered, then Eve has not received any information. And the contrapositive being that if Eve has received any information, then Alice must have decohered to some extent. And the converse also holds because we have this sandwiching. So if Eve has not received information, Alice has not decohered. And so if Alice has decohered, then Eve must have received information. And so there's this quantitative trade-off that really shows that no matter how much Eve could have distinguished these two Coulomb fields, it can't be enough to overcome the decoherence of Alice herself. So that was the flat space story. I'll pause for questions in case these definitions don't make sense or anything else. Okay, so that was the motivation from this flat space Gedanken experiment, and now let's consider doing the same exact thing, except now we think about having a black hole. So in the scenario where we have a black hole, we can have radiation that goes all the way out to null infinity, and we can also have radiation that goes through the black hole horizon. And so we have a more general state that looks like this, where we have some coherent state on the horizon and some state at null infinity and the state of Alice. And the question is, can Alice still maintain coherence if, for example, if she's given a sufficiently long time? Remember, before she could maintain coherence if like QD over the time of her recombination was small. Okay, so this is just the diagram. Think about having Alice following some killing field in the right wedge and separating her particle, and we ask how much, like, can she minimize her radiation through the future horizon and to null infinity? So in this case, even if Alice is given as much time as she wants, Eve can still be at some space, can be behind the black hole, and behind the black hole she can do measurements forever without having any causal contact on Alice's experiment. This means that Alice, so even if Eve does this for a very long time and tries to do it as adiabatically as possible, Eve is going to still be able to gain some witch path information.
Where is he sitting?
So now, so before, so previously, so we wanted Eve to be at a place that can't influence Alice's particle. So in flat space, if Alice is given arbitrarily long time, Eve is really pushed to null infinity. But with a black hole, she can now sit behind the horizon, and she still doesn't have, her measurements can't affect the quantum state of Alice.
But if she sits behind the horizon, she's going to fall into nothing very, very quickly. Okay, what exactly is her world line intended to be here?
Yeah, you can just put her on some world line where she eventually hits the singularity.
Yeah, but then she'll receive signals only for a very short time.
Okay. Yeah, but
I'm not sure this really matters. I'm just not sure the analogy of some actual observer sitting behind the horizon.
It's just saying that somebody in the black hole could make measurements for, maybe this is a short time, but she could still make measurements, and those measurements by the information disturbance trade-off would then
It's not really important that anybody makes measurements, right? It's just important that some information is lost into the black hole.
Yeah, this is when I say making measurements, it's mostly just for intuition. If that intuition doesn't help, yeah, please ignore it. Yeah. There's no one actually making measurements there.
Yeah, nor could there.
Sure, it's just okay. This intuition isn't always okay. It doesn't work for everybody. I agree with what you said. Okay, so but the point being is, regardless of how long Alice has, no matter how adiabatically she does it, there's going to be some region of space-time. Maybe this is a better way to phrase it, is there's some region of space-time she still doesn't have access to, that she has to trace over. And so what's pointed out in this paper last year is that the mechanism for this decoherence is that there's some, that Alice is in a way stimulated in emitting soft radiation that can be measured, or that goes through the black hole horizon at some constant rate. So even though she can minimize the amount of energy that goes through the black hole horizon, she can't minimize the photon flux going through the horizon. And so this can be arbitrarily soft radiation that ends up decoherent. Okay. So to see how this works, consider a classical point charge just outside of a Schwarzschild black hole. The electric field pulled back to the horizon is purely radial. And we call the radiation the pullback of the electromagnetic field, defined like this, so we pick some gauge. Then the Maxwell's equations on the horizon is quite simple. The derivative of E is equal to the affine, so that V is the affine parameter on the horizon. This is the radial part of the electric field. And these capital A's are angular coordinates on the horizon. So yeah, affine coordinate, angular coordinate. And so if the charge is moved, there is going to have to be radiation through the horizon just by integrating this equation. So we integrate this over part of the horizon, and the change in the electromagnetic field, the electric field, corresponds to non-zero radiation. We call this as the radiation. So this is like some dipole moment because the particle has been separated, and there's a different electric field from the two trajectories. Okay, and this ensures that the actual potential must change between early and late times. And you can see that the difference in the electric potential at early and late times is going to be something gauge invariant because it's like an integral of the electric field. So this is what we can think of as the profile for the gauge field. So at some distance, we have some value, and then there's going to be some permanent change in the gauge field. So as mentioned before, the quantum state on the horizon corresponding to this classical charge current source is the coherent state. So I'll call this phi, which is just some Weil operator acting on the vacuum. And the number of photons on the horizon is given by the inner product, which is in frequency space just given like this. So omega times the Fourier transform of A squared. So in this warm-up example where you've separated the charges and just left it like that at all times, at low frequencies this looks like a step function, and so the Fourier transform goes like 1 over omega, and so we have an integral of 1 over omega, and so this is logarithmically divergent, which is this infinite number of soft photons going through the horizon. In our more realistic experiment where we separate the particle and recombine it at some finite time later, the actual number of photons is not going to be divergent, but it will be linearly growing in the proper time of the experiment. So we separate it, it looks like it's this state with memory for a long time, and then it goes back down, and goes back down to its original position at a later time. And the number of photons linearly grows in proper time of Alice times some constants, and so it falls off the farther you are from the black hole. There's an analogous version of this in linearized quantum gravity where you would just have a superposition of a massive particle, and in that case also you would have some linearly growing amount of gravitons going through the horizon.
This is the number of photons and what frequency?
At just total number of photons integrated.
Yeah, but are all of those photons a frequency that's greater than the universe time?
That's greater than inverse.
I mean, if they're zero frequency in this approximation of soft photons, then you can't, you wouldn't be able to measure them in time.
Yeah, they're not zero. They're because we've closed it, so they're just inverse this time. They're only zero in the limit that we just never closed it.
So it's all of their, what are their characteristic frequencies that they set by the time scale?
I think it's inverse of delta V here. Hopefully that's right.
Raphael, it's just the inverse of the time that the particle's displacement. It's held outside with some separation for some long period of
So
time.
delta V.
Delta V is the, like,
time
I mean, the Schwarzschild time outside is, I think it would be T rather than delta V, wouldn't it? Maybe it's delta V. Yeah, sorry, maybe it's.
I think it's delta V just because we're doing the Fourier transform with respect to affine time.
Yeah.
Which is, so exponentially related to Alice's proper time t.
So the fact that the number of photons is proportional to. So in other words, the energy in those photons is roughly fixed. If I think of one photon as having energy 1 over T, the total amount of energy that's radiated into the black hole is independent of delta. At least in the limit theory.
I can't remember off the top of my head exactly like how this is spread in frequency, like where the frequencies are. I would guess that the characteristic would be order 1 over delta V.
The energy per photon is 1 over delta V, then that goes log delta V. So it's log delta V over delta V, so it will go, the total energy will go to 0.
I thought we were measuring it. So T, sorry, V here is an affine parameter, right?
Yeah.
Yes.
At the horizon.
Yeah.
I thought we wanted to measure the energy of the photons that are far away. So I think we want to think of it in terms of T, right?
Yeah.
Oh, the energy, yeah.
The reason I find it a little surprising is that I would have thought that the energy of the photons that get emitted is going to be related to the ramp up time and the ramp down time, not the amount of time that you stay displaced. So I'm a little confused about that.
I mean, that is the key point is that it is about how long you keep it open for, and it's not really about this field. Which from like this, I think just integrating this, I mean, it kind of makes it clear that it doesn't really matter how you do it. There's going to, no matter how slowly you do it, there's going to be some variation. I'll try to get back to you later on the actual, the characteristic frequencies. Okay, so if it's okay, I'm going to move on and talk about now a bit more of a local understanding of Alice's decoherence from the radiation of this very soft radiation. And so we want to have a generalization of the overlaps that I was discussing before, but for mixed states we don't have overlap, so we replace this by this fidelity that I was mentioning. So now we want to have a more local analysis in time, where we say that up until this point of time, Eve is able to make measurements of Coulomb field, and this propagates back, and we're then learning at this point in time in Alice's experiment how much is she decohered by that time. So to make these, to actually do these computations, we need a few elements of Tomita-Takasaki theory, which is I'll say the basic elements. We have this Tomita operator, which maps elements of Eve's algebra. So basically, just any operators in this yellow region, it takes them to their emission conjugate acting on the other state, and and then the modular operator is just this S stagger S. So this is like the analog of the density matrix. And the fidelity we compute is simply just the modular operator, the square root of it, the expectation of value of that in this state. So as I mentioned, the states that we're considering on the horizon are coherent states. So this is just taking the vacuum state and then acting some unitary on it. And so in these simpler cases, this relative modular operator is related to the modular operator of just the vacuum state that's just conjugated by some unitary operators. And so plugging this into this fidelity equation, you can see that the fidelity will be completely independent of the quantum state that's at a later time. So up here, there's some quantum state, but Alice doesn't have access to it, and you can just see that from the formulas that the amount she's able to distinguish these two paths is independent of what's going on in this later region. Okay, so yeah, from this picture, we're thinking of Eve only having access to the state up to some finite time, and wondering what the fidelity is.
So where do this experiment? It's on a black hole background.
Yeah, it's on a black hole background.
And then some constant R, splitting into some different constant R.
Yes.
Then this should be, because it's acceleration, it's photon radiation to go to the linearity. Then the frequency must be equal, so frequency must be equal to temperature at the rotational distance.
So if you just consider the green line, there's going to be no radiation. Like from this kind of acceleration, there will be no radiation.
So you really have to separate it.
You have, it's when you're separating it, then there's radiation, but when it's following the trajectory, there's no radiation.
Still something equals linearity.
Yeah.
I'm confused about the following issue. Correct me if I'm not allowed to reformulate the problem in the following way. So to get decoherence, due to stuff falling into the black hole, I would need to have at least about 1 qubit of information fall into the black hole, since I'm trying to distinguish between lots of and so we can just think about what that means for the black hole. If you add that much information to the black hole, the area should go up by order 1 in terms of by about order 1 in Planck units, and so given the original size of the black hole, that corresponds to sort of adding 1 multi-quantum to it. It's a fixed amount of energy, but it depends on the mass of the black hole that you started with. It's going to be more of a small black hole. I'm confused about several things here. One, that the mass of the black hole seems to play absolutely no role in your analysis. Where does that come in?
So the mass comes in.
Oh, it's a prefactor.
Yeah, it's a prefactor.
And would you say that decoherence occurs when n phi is greater than 1?
Yeah, when it becomes order 1, that's when decoherence would happen. Because yes, as we find decoherence, it's like 1 minus e to the negative n.
Okay, thanks. I would love to understand how your results will, whether they can be related to that way of thinking about it.
Yeah, I guess one thing is we're not considering any back reaction. We haven't
Well, neither is my argument, but I'm just saying that we know that a change in area of one can be translated into a certain amount of energy that would have to be radiated into the black hole.
Okay, the remaining hard part of this formula is knowing what this modular operator is, but because now it's just the modular operator for a vacuum state, this is one of the few things people actually know, and it's just given by boosts. So this is the Physignano-Wickman theorem and its generalizations to, for example, this eternal black hole, the Hartle-Hawking state. So really, everything comes down to just computing the expectation value of some finite boost in some coherence state. And because we take this to the 1/2, we just need to do some analytic continuation in this boost to some, Euclidean rotation. But this analytic continuation is totally safe. There's no ambiguities, and you can do this, which is guaranteed by the KMS property of the Hartle-Hawking state. So you get some kind of ugly final expression in terms of the fidelity as a function of time. Okay, but it's explicit, and you can see that because of the rapid oscillations, as V0 gets large, so as this cut gets later and later, this will just end up becoming this number of particles that I had earlier, so e to the minus number of particles. And so just by thinking about monotonicity of fidelity, so fidelity can only decrease in time. This makes it a good measure of distinguishability. And by thinking like that, you can say that the fidelity at a fixed point in time is at least bounded by the number of particles, or e to the minus number of particles that have been emitted up until that point in time. And in some way, the black hole is acting like an optimal measurement. When you trace it away, you have to consider any sort of measurement that could have been done on the auxiliary space. So yeah, that's what I wanted to say with the black hole story. And now let me mention that in this paper they also looked at other killing horizons. So you could think of just doing the same experiment in the static patch of de Sitter. And here, okay, this is really some geodesic, so there's no confusion about radiation of the actual static particle, but you'll still get the same effect in terms of radiation going through the cosmological horizon. And you could, if you want to, you can think of Eve sitting behind the cosmological horizon trying to decohere ions. So the calculation of fidelity is completely the same. But if you're interested in the number of particles, in this case, and how it scales with the Hubble constant, then it's like this. And in the gravitational case, it drops off faster. So I'm going to end with some more necessarily speculative remarks. So from the perspective of quantum field theory in curved space, we've been thinking about Hartle-Hawking state, some vacuum solution. So it might be surprising that black holes are good absorbers of radiation at really low frequencies, frequencies that are much lower than just the inverse Schwarzschild radius. What's been called the central dogma of black holes is that we shouldn't think of, or that in the UV we can think of black holes as some highly excited, chaotic quantum objects with e to the s degrees of freedom that are just evolving unitarily. So this experiment is, I think, consistent with the idea that black holes are like highly excited states, where lower the frequencies can be efficiently absorbed. So if I take a chunk of metal and I look at the energy spectrum of my metal, if I'm near the ground state or I'm in these low excited states, I have large energy gaps, and so you're not going to absorb low energy frequencies. But if you're up near this continuum, where people think, there's reasons to think black holes are more like highly excited quantum objects, the level spacings are quite small, and it's not as mysterious to think about black holes as being really good absorbers of these very low frequency radiation. From this perspective, and the fact that you can do the same story for ADS black holes, it might be interesting to express all of this in terms of CFT variables, because then you could start to probe some quantum gravitational effects beyond the limit of what we've been able to do. That's all I have. Thank you very much.
Questions for Jonah?